All right, here's what we've got going on today. We're going to be talking about Riemann sums, which are something we've actually already talked about in the previous video, except we didn't call them Riemann sums. And then we also tried to segue out of the last video, introducing the idea of, instead of finding the approximate area by using a finite number of rectangles below a curve on an interval, instead using an infinite number of rectangles and getting, therefore, an exact area under a curve. You could write the formula for approximating an area under a curve using a finite number of rectangles in the following way. I'm hoping you can make heads or tails of this. If you can't, don't worry, I will explain each part. But the key is to not get scared, because you actually know what all of this fancy looking set of symbols, variables, and other means. Let's start with b minus a over n. b minus a is the width of the interval, because that's subtracting the endpoints gives you the width of the interval. Dividing that by n, which is dividing it by a number of rectangles, gives you the width of a single partition. A single rectangle width in this region. To get the height of one of the rectangles, you have to plug an x value into the function. We get the heights of the rectangles based on the heights of the function. And we get the heights of the function by plugging stuff in for x into the function. That's why we have f of something to get the heights of the rectangles. You start with the leftmost endpoint, and each subsequent x value that gets plugged into the function is a rectangle width further down the road. The I dictates that you keep increasing each rectangle width by 1 unit every time. The result will be the height of each rectangle. And then ultimately, you want once you have a width and a height and they get multiplied together, that gives you an area of a rectangle. Well, you want to add up all the areas of the individual rectangles. That's why there's a summation sign. All this working in conjunction, we did this yesterday, we did this in the last video. This is the concept known as a Riemann sum. A Riemann sum is named after George Riemann, who was a German mathematician. And what we're going to be doing is taking this approximation and using infinite rectangles to get an exact area. In order to do that, we show the limit as the number of rectangles that we're using approaches infinity. That will make the sum a sum of infinite areas instead of finite areas. And that's what makes our answer exact instead of an approximation. All right, I'm going to transfer this formula onto the next page, and we can maybe tackle an example. We're going to determine the exact area under the graph of this function, which is an upside-down parabola, over this interval. And the first thing we need to do is figure out how wide would each rectangle be. The width of a single rectangle will be the width of the interval divided by the number of rectangles you're using. b minus a over n, in our case, is 3 minus 1 over n, or 2 over n. We're going to leave n as n because we're going to eventually have a limit. N's going to be very large. We're just going to leave the number as n. It's a constant. That's going to be important throughout this problem. N is a constant. Even though it's really big, it's still a constant. Therefore, our area, using the formula up here, 2 over n goes in for our b minus a over n. They use f of, we're going to use y of. That's just how it was given to us as a y variable, not an f of x. Start with your left endpoint. A is 1. Add on the width of a rectangle I times. That's how this thing sets up. And honestly, boom, we're done with the calculus. the next 80 billion steps that this problem is going to take, and if you don't believe me, look at the runtime on this video, the next 80 billion steps are all going to be algebra. Here we go. Transferring this onto the next page. The first thing I'm going to do is get rid of y of something. If it said y of 3, I would plug 3 in for x. If it said y of 6, I would plug 6 in for x. Well, it says y of weird thing, so I'm going to plug weird thing in for x. That's all I'm going to do on this next step. When you do, you get something like that. So the y of whatever is gone, and just the result remains. I see a lot of people sometimes will make the substitution, and then they'll put y of it. But the fact that you plugged something in for x in the y function means you need to cease writing the y part. It's like if you have f of 3 and you get an answer 6, you wouldn't say f of 3 equals f of 6, you just say f of 3 equals 6. So if you have y of something equals something, drop the y. Our next step is also another common algebra mistake people make is they see this 2 exponent and they say, oh, distribute that through. But you can't distribute exponents. You can do one of two things here. You can either write down, do a little side work, say 1 plus 2 over ni times itself, because that's what it means to square something, and then you could FOIL it out. Or, if you know the shortcut for squaring a binomial, a plus b quantity squared is just squaring the first thing and squaring the last thing, like people do when they quote-unquote distribute exponents, but it's also including the meat of the sandwich, which is that 2ab term in the middle. So putting this in for this, and everything else staying the same, gives you something that looks like that. So now this trinomial has gone in for the binomial squared. And our next step is as easy as it looks. I'm going to distribute this negative, or this subtraction, into all 3 terms that it's affecting. In doing so, of course, we get something that looks like that. The next step's also a bit of a no-brainer. You can see that there's a 16 and a negative 1 that will combine. And also, this 2 over n, this is a constant. If 2 is a constant and n is a constant, n is just a flat number of rectangles, then 2 over n must be a constant, and it can be written as a constant out front of the summation. So I'm going to do both of those things in this next step, and doing so would give me something that looks now like this. So the 16 minus 1 is combined to 15, and the 2 over n is now happily outside the summation. So now the fun starts. I'm going to give each term its own summation sign. So I've still got my limit as n approaches infinity out front. I've still got my 2 over n pulled out front, and then I just use brackets. Instead of writing a 2 over n in front of each set of, or in front of each summation, I just use brackets for the whole thing. And I've got summation of the first term, I've got summation of the second term, and I've got summation of the third term. From here, we can apply summation shortcuts. Remember we had a summation shortcut for summation of a constant, summation of I squared? Well, it's about to come back. Here's what happens. The summation of 15 is the summation of a constant. The result is just the constant times n. 4 over n is a constant, so I kind of pulled that quote-unquote out front, and then I just focused on summation of I, which results in this n times n plus 1 over 2 pattern. Summation of 4 over n squared, that's a constant, so I pulled that out. And then I can just focus on summation of I squared, which results in this pattern. And it's really just algebra, algebra, algebra from here on out. That's what we just saw, rewritten now on this page. I am going to distribute 2 over n into each term. And at the same time, I'm also going to make this this fraction times a fraction, I'm going to make that a single fraction bar, make that a single fraction bar as I distribute the 2 over n into each term. Doing so gives you something like this. 2 times 15, that's your 30. The n over n shows up in the fraction. 2 times 4, that's where the 8 comes from. There was already an n there. You have an n plus 1 over essentially 2n times this n is where the 2n squared comes from. And then here, 2 times 4 gives you 8. There was already an n there, that carries over. These quantities carry over. And then underneath we have 6n squared times another n is where the 6n cubed comes from. More algebra, algebra, algebra. I got sick of typing, so I'm going to handwrite this. Start out with my limit as n approaches infinity. The 30n over n, the n's are gone. It's really just 30. So I'm going to start out with a set of parentheses because I'm taking the limit of several terms. I've got a 30. In my next term, I can simplify. 8 halves is 4 over 1. N over n squared is just an n in the bottom. Do not cancel this n with that n. This n is a single term, whereas this n is a factor. You can only cancel factors. At the same time, I'm going to distribute this 4 into the n plus 1, giving me 4n plus 4 over n for this second term. In the final term, 8 over 6 is 4 over 3. N over n cubed is 1 over n squared. Now this is a little more of there's a lot going on in this term. So I'm going to, well, I'll still distribute this 4. I got 4n plus 4. It's still factored because both of those have to get multiplied by the 2n plus 1. And the whole thing is over 3n squared. And that'll close off that step. Now, more simplifying. And then, there's one of any million ways you could go on this. I don't have to do this in the exact same order I'm doing it in. I don't even do it in the same order every time. Just have to get all the steps in there somewhere. What I'm going to do next is I'm going to get rid of this fraction. I'm going to get 2 terms out of this fraction, so it's important to remember to use parentheses to show that this subtraction sign affects both of the terms that come immediately after it. What I'm going to do is I'm going to simplify 4n over n as just 4, and then 4 over n I will keep as 4 over n. But if without these parentheses, this minus, the subtraction, will not affect this second term the way it should. Same thing, well, you know what, before I even get to that on this last term, I'm going to foil this out. We get an 8n squared when we do first times first. 4n on this loop plus 8n here gives me 12n when I combine them, and this is a plus 4 term at the end. And then I am going to write this as 3 separate fractions. 8n squared over 3n squared is nothing more than 8/3. 12n over 3n squared is nothing more than 4 over n. And then 4 over 3n squared is quite literally 4 over 3n squared. Notice all 3 terms are in a set of parentheses, so the subtraction sign out front of the fraction affects those 3 terms even when they're not written as a single fraction anymore. We're almost there, ladies and gentlemen. We've got 30 minus 4 over n minus 8 over 3 minus 4 over n minus 4 over 3n squared. We are now ready for the direct substitution step, where we actually let n approach infinity. Doing so gives us 30 minus 4. 4 over n becomes essentially 0. Minus 8/3. Minus 4 over n becomes essentially 0. And 4 over 3n squared becomes essentially 0. When you add all this up, 30 minus 4 is 26, minus another 2 2/3. So let's see, 26 minus 2 is 24, minus another 2/3 would be 23 1/3 square units would be the actual area under the graph of this curve on the given interval. Obviously a lot of steps here. A lot of little places you could make mistakes. I will be looking for all those mistakes because that's what I do. So try not to make them. The big things to look out for are knowing your summation shortcuts for constants, for I squared, remembering your parentheses, and avoiding the temptation to distribute exponents. If you can overcome those three obstacles, you'll be putting yourself in a position to do well in this section. Of course, eventually we're going to talk about shortcut ways of doing all this, but not before we revel in the long cuts for a while.